Hello everyone, here is Weixuan Sun from the Australian National University. I will introduce our work, Inferring the class-conditional response map for weakly supervised semantic segmentation. In this work, we focus on the image level weakly supervised semantic segmentation. It is challenging as we are using image level labels to supervise pixel-wise predictions, as shown in the image below. So there is an inherent gap between them. To fill this gap, current weakly supervised semantic segmentation methods adopt a multi-step pipeline based on the class activation maps. First, they retrain the classification model to generate CAMs. Second, they post-process the CAMs to obtain pseudo-labels. And finally, they train a semantic segmentation model with the obtained pseudo-labels. So the quality of the CAMs is very important. In this work, we propose a method to generate better CAMs for weakly supervised semantic segmentation, as shown in the image below. Better class activation maps lead to better segmentation pseudo-labels and will improve the performance of semantic segmentation. As most current weakly supervised semantic segmentation methods aim to obtain better CAMs by retraining the ordinary classifier, our method works with an ordinary trained classification network fixed and does not require retraining this classifier, which means that our method can be implemented in the inference stage. We first revisit class activation maps. We have one key finding in our work. The ordinary trained classification model have already learned sufficient features and are able to activate the entire object, as shown in the image below. Thus, the main issue of the CAM is not in their sparsity and incompleteness, such as they only focus on the discriminative regions, but is overcomplete and uneven, as discriminative regions suppress the activation of other regions. Thus, we argue that retraining the ordinary classifier is not necessary. Based on our finding, we propose two methods to leverage the power of the trained classifier. First is split and unite image augmentation. Second is iterative inference. Our method does not require retraining the classifier. Finally, we also propose the activation-aware mask refinement loss, which is a new approach to incorporate the saliency information in the weakly supervised semantic segmentation training. In split and unite image augmentation, first we obtain the baseline CAM and calculate the mask center of the CAM, as the mask center always locates on the objects. Then we split the image into 4 patches according to the mask center, so each patch contains a part of the objects. Then we do CAM inference on each patch separately, as discriminative regions is computed individually in each patch. When any suppression elements in the other patches are removed, we can locate more discriminative areas on different object paths. Then, in the iterative inference, we iteratively do inference on the image. In each iteration, the high activation regions from last iterate are erased. Without that suppression, more areas are progressively activated. Then we combine the activation regions of every iteration. Unlike other methods, in this process, our network is fixed without training. Finally, we combine above two methods together, and our proposed module can be seen as an add-on module, so it can be seamlessly utilized in the inference stage of any pre-trained classification network. Finally, we propose activation-aware mask refinement loss. Saliency maps are often used as a background cue in pseudo-segmentation labels, but we find that there is an inconsistency between the saliency map and the pseudo-labels or the ground truths. The saliency maps may falsely detect non-object salient areas in the foreground and tend to ignore non-salient objects in the background, as shown in the image below. So it may introduce errors and harm segmentation training. To deal with above issue, we propose to use saliency map as a subsidiary loss during the training, and we use a consistency between the saliency map and the pseudo-label to control the weight between two losses. Please see more details in the paper. Here are some qualitative results that we can generate better CAMs and lead to better semantic segmentation results. Quantitatively, our CAM and pseudo-labels outperform the competing weakly supervised methods, and also our final semantic segmentation results achieves the state of the art. Thank you.